I'm assuming that you have a textbook to use to follow along with us. We use a free online textbook called OpenStax. So the material we're studying now is roughly in sections 5.1 through 5.3 of OpenStax University Physics Volume 2. And I'll try to put in the top of each page in the start of the video roughly what sections we're covering from the textbook. Now we're going to talk a little bit about charging by induction. So in the last video, we saw that we could induce a charge separation in an object by bringing a charged object next to a neutral object. We could get that charge separation. Charging by induction takes that one step further so that the object actually becomes charged. We'll start out with a conductor. I'll make mine a sphere. And that conductor is electrically neutral. There are lots of charges in that conductor, right? Every atom inside the material that makes up that conductor has positive charges at the center in the form of protons, and it has electrons around the outside. And because it's a conductor, those electrons are free to move around. But for every positive charge, there's a negative charge. So we have an electrically neutral conductor, but remember, there are lots and lots of charges inside this conductor. Now we're going to bring a charged object up next to the conductor. Those electrons are going to reposition themselves. When we bring a positively charged rod up next to that spherical conductor, or any conductor for that matter, the negative charges that are free to move around, the electrons in that conductor will move. They're attracted to that positive rod. So we end up with some excess negative charge on one side of the conductor. And that's going to leave some unshielded protons back here. So some excess positive charge on the other side. Of course, there are lots of atoms all throughout the solid conductive material, and there are positive charges and negative charges surrounding all those atoms. But what we care about is the electrons that move, and it turns out that they move from one side to the other. If you want to think about it this way, the logic is the same. The positive charges want to move away as far as they can from the positively charged rod. Now we know positive charges don't move, it's the negatives that move, but sometimes it's a little easier to think about it that way. Of course, the conductor is still electrically neutral, has the same number of positives and negatives. We just induce this charge separation. What would happen if we allowed more electrons to enter or leave this sphere? Let's ground it. Let's attach this side of the sphere to ground. That's the symbol for ground. Ground is like a huge reservoir of excess charges. What's going to happen is that the electrons from ground, from this huge reservoir of excess charge, will come up. They're attracted to the positive charges over here. And so we're going to get electrons that come up and add to the sphere until they exactly cancel out those positive charges on the right side of the sphere. If you want to think about it as positive charges moving, the positive charges were repelled by the positively charged rod, so they went as far away as they could get. And when we grounded it, they could go even farther away, so they do. They leave the sphere. Of course, it's the electrons that are attracted to this positive rod next to the sphere. They attract the excess electrons up. So when we remove the ground, the conductor now has excess negative charges, and it's a charged object. So this is called charging by induction. We can induce a charge separation, ground the object and allow some of the charges to leave or charges to enter, and end up with a charged object. Last class we saw that we could get charged objects by rubbing dissimilar materials together and get transfer of electrons. And now we're seeing another method when we can ground a conductor while there's a charge present and that gets excess charges to enter or leave the conductor. Remember that in order for charge to transfer, as far as we're concerned in this class, the objects have to have physical contact. They have to be touching. We know that charges can jump across air gaps, right? That's what a spark is. That's what lightning is. Charges can flow across air when the air breaks down and becomes a conductor. But for the purposes of this class, we don't think about that situation. We're looking at, for charges to get transferred, for objects to become electrically charged, there has to be physical contact. They have to touch one another. Now that we know how we can make objects electrically charged, let's think about what happens to these charged objects. How do they interact with each other? Well, they interact with forces. They can exert forces on one another. We already saw that charges that have the same sign repel each other. They exert repulsive forces. And objects that have opposite signs attract each other. They exert forces on each other that pull them together. They attract one another. So let's look at that force in a little more detail. Let's look at Coulomb's law. Coulomb's law tells us how to find the force between two charged objects. Let's think about what we would expect the force to depend on between two charged objects. Well, it would depend on the charge, right? The charge on one of the objects and the charge on the other object. The charge, we use Q for charge. And what else might it depend on? How about the distance between the charges? As the charges get farther and farther apart, we would expect the force to get weaker and weaker. So that would be an inverse relationship. And it turns out it drops off as the square of the distance. So that would be 1 over r squared. Now we want to have an equal sign here. We know the force is proportional to the charge on one of the objects. It's proportional to the charge on the other object. It's proportional to 1 over r squared. But we want to have an equal sign in there, so we need a proportionality constant. It turns out that constant is 8.99 times 10 to the 9th. Our unit for electric charge is the Coulomb, capital C. That's why I have Coulomb squared there. That's the unit for electric charge. And we use the symbol Q to signify charge on an object. Some books write this as K sub E for the electric constant, and some books write it as 1 over 4 pi epsilon naught. Epsilon naught is a constant that we have in physics, but this is just equal to we got tired of writing 1 over 4 pi epsilon naught all the time and just started writing K. This should look somewhat familiar to you if you remember back from your mechanics class. The force of gravity was proportional to the mass of one of the objects, and it was proportional to the mass of the other object. It was inversely proportional to the square of the distance between the two objects. And in order to get rid of the proportionality sign and put an equal sign in there, we had a constant, a universal gravitational constant G. Of course, with mass, we only have one kind of mass. So this force is always attractive. The two massive objects always attract each other because of gravity. With electric charges, we have two different signs, and we can get a repulsive force or an attractive force. I typically write my equation the way I wrote it here, as the magnitude of the force is the magnitude of the charges multiplied together, and I just take absolute values, come up with the magnitude of the force, and then I look at the situation and figure out what direction the force is and assign a direction to it. Because of course force is a vector quantity, and for your answer to be complete, you need magnitude and direction. There's another similarity between the gravitational force and the electric force. When you took mechanics, the only force you learned about in mechanics that could interact at a distance was the force of gravity. Two objects don't have to be touching each other to exert forces on each other through gravity. But they do have to touch each other to exert a frictional force on each other. A rope has to touch something to exert a tension force on it. All the other forces we learned about, there had to be some contact there between the two objects, except for one, the force of gravity. So now the electric force that we're learning about, it's the second force that we're learning about that can interact at a distance. It's just like gravity in that respect. And it's hard to kind of wrap our minds around that. How can these two objects interact with each other without touching each other? So we need a model. We need something that'll help us wrap our minds around that and sort of sort that out and explain to us how that might be possible. And our model is fields. We say that a massive object fills the space around it with a gravitational field. And any other massive object in that field interacts with the field, and it feels a force because of that interaction. So this object will fill the space around it with the gravitational field. And what direction does that gravitational field point? It points in the direction a mass would go if we put it there. So if we put a mass out here at this location, it would go in that direction. The gravitational force is an attractive force. So the gravitational field points in toward this object. I'll put arrows on all of these gravitational field lines, and I'll label them. We do the same thing with electric forces. We say that if we have a massive charged object, let's make it positively charged in this case, it fills the space around it with an electric field. And any charged object in that field interacts with the field, and it feels a force because of that interaction. What direction do our electric field lines point? Somebody had to pick a direction. So our convention is that the electric field lines point in the direction a positive charge would go if it was sitting at that location. So if I stuck a positive charge here, it would be repelled by this massive positive charge at the center. It would go outward. So that's the direction my electric field points. It points away from a positive charge, and it points toward a negative charge. So I'm going to go ahead and put arrows on my electric field lines. Electric field lines. That means that if I replace this massive positive charge with a negative charge, that negative charge also fills the space around it with electric field lines. But if I put a positive charge there, it would be attracted to the negative charge. So the field lines around a negative charge point to the negative charge. Let's think back to last quarter when we were dealing with gravitational fields and gravitational forces. I used capital M for the mass of my big object that was creating the gravitational field, and I used lowercase m for the little test mass that we're putting in the gravitational field that's feeling the force because of that field. So let's come down here. The force that's experienced is G m over r squared. We get tired of calculating this every time we have a mass in the same situation, right? So let's think about what happens on the surface of the Earth. This is how we would calculate the weight of an object on the surface of the Earth. The weight of an object is the gravitational force between that object and the Earth. So we could do this calculation every time, but we get tired of doing this calculation every time because the mass of the Earth doesn't change. G is always the same, that's a constant. And r, the radius of the Earth, doesn't change. Every time we weigh something on the surface of the Earth, we're on the surface of the Earth. The distance from the Earth is the same. The only thing that's changing is the little m, the mass. Maybe I'm trying to calculate the weight of this pen. Maybe I'm trying to calculate the weight of this cup. That's the mass that's changing to find the force, the weight of the object. So I could write this as F, the force, is equal to the gravitational field times the mass of the object. Maybe you remember it as mg. F equals mg, weight equals mg. What is g? What is the gravitational field? It's g times the mass of the Earth divided by the radius of the Earth squared. That's what g is. So let's do the same thing. This, I'm going to label it here, gravitational field. Let's do the same thing with the electric force. Just like I did with the mass, I'm going to use capital Q for the charge of the big charge that's creating the electric field. And I'm going to use lowercase q for the little test charge that I'm putting in the field that's feeling the force because of that field. So my force, K, Q, Q over R squared. And I don't want to have to calculate this all the time when Q, capital Q, and R aren't changing. If the only thing that's changing is my lowercase q, I don't want to have to calculate this every time. So I want to do the same thing I did with gravity. I want to say the force is going to be equal to some electric field times the charge that I'm putting there. And how do I find the electric field for a point charge? The electric field is K, Q over R squared. That's for a point charge. Remember, these are vector quantities. So charge has no direction, that's a scalar, but electric field and electric force both have direction, and the force and the field point in the same direction. I'm going to rewrite it down here. I'm going to say F is equal to Q E. So if the Q is positive, then the force and the electric field point in the same direction. If the Q is negative, it flips the direction of the field by 180 degrees, and the force points in the other direction. So this equation is always true. F is equal to Q times E. The force on a charge is equal to the charge of that object times the electric field that exists at that location in space where the charge is located. That's always true. This second part, the electric field, is equal to KQ over R squared. That part is only true for a point charge. We use that a lot though. The electric field is KQ over R squared from a point charge. The charge on that point charge is Q, and the distance is that we are away from it is R, and that gives us the electric field at that location. We often have other charge configurations. We don't just have point charges. We might have a whole line of charge or a sheet of charge, and we're going to learn how to calculate electric fields from those distributions also. But we're going to start with this one, electric field from a point charge.